Let's begin with Newton's second law that we're accustomed to, and that is force is equal to mass times acceleration, or net force is equal to mass times acceleration. Let's replace the linear variables with their angular equivalents. So the angular equivalent of a force is a force that produces rotation. That's torque. The angular equivalent of mass is moment of inertia I, and the angular equivalent of linear acceleration is angular acceleration alpha. Let's prove this. We know that a linear force produces a linear acceleration. So that's for angular or circular motion, that's the tangential force produces a tangential acceleration. And we know that torque is equal to tangential force times R. So if we say torque is tangential force times R, and we replace Ft with mass times At, and we also go a step further and replace At with R alpha, then we see that torque is equal to mr squared times alpha, and when we say the net torque, it's the sum of all the torques, and we know that the sum of all the mr squareds is the moment of inertia I. And so we prove that the net torque is equal to moment of inertia I times angular acceleration alpha.
So here's my spindle. It can rotate, and I've wrapped a string around it. So when I hang a weight from the string, the weight of this mass produces a torque. And right here, between the axis of rotation and the outside edge of the spindle where I've wrapped the string, this is my R perpendicular. This is my moment arm. So according to my equation, torque is equal to force times R perpendicular. The tension in the string times the moment arm R produces a torque, which causes the spindle to accelerate. Now, how much it accelerates here, how much it accelerates depends on the torque, but it also depends on the moment of inertia. And I know here, moment of inertia is determined by not only how much mass there is, but how far the mass is from the axis of rotation. These masses here, they're adjustable. I can loosen it and adjust how far away it is from the axis of rotation. In other words, I can change the moment of inertia of this object. So if moment of inertia goes up, that means alpha will go down, and vice versa. If moment of inertia goes down, alpha will go up. Let's see this in an experiment.
So in our experiment, I've got the setup shown side by side here. On the left side, the masses have been adjusted so that they are fairly close to the axis of rotation. And on the right side, I've adjusted the masses so they are at the extreme ends of the arm. So in other words, my setup on the right has a larger moment of inertia than the setup on the left. And we're going to time and see how long it takes to rotate 5 times. We'll use this weight here. It has a piece of tape with a line drawn on it so we can measure how many times it goes around, and we're going to time how fast it takes for 5 rotations. Here we go. I release them both at the same time, and we can see right away that the setup on the left with the lower moment of inertia has a much greater alpha, only taking 9.4 seconds to rotate through 5 rotations. And on the right, it took 15 seconds. So the further the mass was away from the axis of rotation created a larger moment of inertia and a lower alpha. Over here, a higher alpha with a lower moment of inertia.